Hydroelectricity is a well-established technology. It dates back to the beginnings of the electric power industry more than 100 years ago. About 7% of the electric power now generated in the United States comes from our damming the rivers as they flow to the ocean and then releasing the water to turn turbines connected to the electric generators. The available energy of water stored at a height above a generator is potential energy in the Earth's gravitational field. The solar energy that went into lifting the water upward in this gravitational field can be made available again when, for example, the water falls downward onto a water wheel. As each element of water of mass m falls freely a distance h, it attains a velocity v and kinetic energy 1/2 mv squared, equal to its original potential energy, which is given mgh.
Hydroelectric power plant. In a hydroelectric power plant, electricity is produced from water. A dam is built across a large river to hold back the river water and raise its level to form a reservoir. At the bottom of the dam, there is a floodgate. Water flows through the penstock and rotates the turbine. The flowing water rotates the turbine, which is placed at the end of the penstock. The turbine, in turn, rotates the shaft that is connected to the coils of a generator. These coils are placed in between strong magnetic poles. The rotating shaft turns the coils. The change in magnetic field due to the movement
Electrons are able to move from atom to atom. When the movement of electrons is in mostly one direction through an object, the movement is called electricity. A magnetic field can be used to produce electricity. In fact, magnetism and electricity are really two permanently related parts of one fundamental force called electromagnetism. Every time there is a change in magnetic field, an electric field is produced. Electric current can also be used to produce magnets. Around every current-carrying wire is a magnetic field created by the uniform motion of electrons in the wire. Voltage, V, is a measure of the pressure applied to electrons to make them move. It is a measure of the strength of the current in a circuit and is measured in volts, V. Electrical current is the number of electrons flowing past a fixed point in a certain amount of time. Current is measured in amperes or amps. 1 ampere is 6.25 times 10 to the 18th electrons per second passing through the circuit. Resistance, R, is a property that slows the flow of electrons, the current. Resistance is measured in the units called ohms. There are devices called resistors with set resistances that can be placed in circuits to reduce or control the current flow. Every load in a circuit has resistance. George Ohm, a German scientist, discovered that in many materials, especially metals, the current that flows through a material is proportional to the voltage. In the substances he tested, he found that if he doubled the voltage, the current also doubled. If he reduced the voltage by half, the current dropped by half. The resistance of the material remained the same. This relationship is called Ohm's law and can be written in 3 simple formulas. V times I times R, where V is for voltage, I is for current, and R is for resistance. Electrical power is defined as the rate at which electricity is converted to another form of energy. It is the amount of electricity required to start or operate a load for 1 second. Electrical power is measured in watts, W. The formula of electrical power is power, watts, equals voltage, volts, times current, amperes, or P equals V times I.
Hi guys, today I'll be explaining about electromagnetic induction. The reason I chose this topic is because electromagnetic induction plays a big part in our technology, especially in the regions of electric motors, which are used extensively today. It all began in 1831 when a scientist named Michael Faraday he discovered electromagnetic induction. He then proposed Faraday's law, which states that when the magnetic flux linkage in a circuit changes, an electromotive force is induced in the current. To explain this, I can show you by two bar magnets with a magnetic field in between them. When a wire is run through these two bar magnets, this causes the magnetic flux linkage to change and then a current is induced in the wire. I shall now explain electric models. To understand the concept of electric models, we need to use Fleming's left-hand rule, which then if you take up your three fingers, you can surely show that the thumb can represent the force, and the index finger represents the magnetic field, and the middle finger will represent the current.
The device that I have here is a generator. Let's see what parts it has. I can turn the crank here. When I turn the crank, what it does is turn an armature inside. Now, an armature is a coil of wire that's specially wound, and it turns in a magnetic field. And the purpose, of course, as you know from generators, is to generate electrical current. Now, you can't see the armature inside there, so I'm just telling you about it. Also inside here are a series of gears, and the purpose of the gears are to increase the rate of rotation of the armature compared to the rate of cranking. So I can crank slowly, and I could get a very rapid rotation inside the armature. The output of the generator comes through these two wires, so if I clip this to something external, such as a light bulb, I will get electrical current going through the light bulb.